Welcome to our lecture on probability.
It's really very difficult to define probability. The best way to see it is you see how often this event will occur in the long run. For example, if you keep tossing a coin over and over again, you'll note that 50% of the time you'll get a head. So we say the probability of the head is 0.5. So think of it that way, but really there's no good definition of probability. Now the difference between probability and statistics. In probability, the population is known. You know what mu is going to be. We talked about this. Mu is NP. You toss a coin 100 times, you're supposed to get 50 heads. In statistics, you don't know the population parameters. So you got to make an inference. You take a sample, and from the sample, you can make an inference to kind of estimate the population parameter.
The definition of the probability of an event that we just saw is an objective probability. It's the classical mathematical definition of the probability of an event as the long-run frequency of occurrence of a particular event. On the other hand, a subjective probability is the kind of probability we might use in ordinary conversation that's not based on mathematics, and it measures the strength of our personal beliefs. For example, if someone says, as a personal opinion, the probability that this new product will succeed is 95%. That's the strength of a personal belief. Or even better, maybe, the probability that my commute will not exceed 1 hour tomorrow morning is 90%. Right? I haven't exactly computed that, so it measures the strength of my personal belief. That which is observed as the result of a stochastic or probabilistic process is a random variable. A random variable takes on values. Each of these values has a probability. Each is related to an event. The event is the value that the random variable takes on. So, for example, when we toss a die, that's a process. It's a probabilistic process. We could get a 1 on the face of a die. We could get a 2. We could get a 3. There are 6 possibilities. Assuming the die is fair, they're all equally likely. So each one of those has a probability of 1/6. A simple probability, as we'll see soon, that's also called a marginal probability. That's the probability of an event. It's just we're looking at one event, and we're looking at the probability that that event will occur. A joint probability is the probability of 2 events occurring together in time or space. A conditional probability is the probability of an event where we have some information about some other event having occurred. So if we know that B is true, and we're asking about the probability of A, that's a conditional probability. It's the probability of A, given that we know B, that B has occurred. Here are some basic rules about probability. The probability of an event will never be less than 0. It will never be negative. It will never be greater than 1. It can't be, by the definition of a probability. A probability is exactly like a proportion, which also can't be negative and can't be greater than the total, than 1. So if you tell me that the probability that you will pass this course is 150%, you're starting at a disadvantage here right away. Rule 2. The sum of the probabilities of all possible outcomes of a particular process must equal 1. So the probability of A and the probability of everything that's not A together, that's got to be equal to 1. The probability of getting a 1 on the face of a die, or a 2 or a 3 or a 4 or a 5 or a 6, those are all the possible values. Can't get anything else. You add those up, that has to be 100% or a 1. If the sum of all your probabilities is less than 1, what does that mean? It means you're missing something. You're probably missing an event you forgot about or an outcome. If it's more than 1, that's a little bit more complicated, and it probably means that the events you're looking at, that there's some overlap. That maybe you're looking at the probability of getting an odd number and then the probability of a 1 at the same time. Well, there's overlap there.
Before we get to the rule of addition, let me define something called mutually exclusive. Mutually exclusive has the word exclude in it. It means two events that can't occur together, like heads or tails. You can't have a head-tail, male, female. It's one or the other. You can't have both simultaneously. All right? When two events are mutually exclusive, let's call them A and B. If they're mutually exclusive, the probability of A or B, notice we have two different ways of showing it. Some books have that U symbol. Okay, but I'll probably use the word or. Probability of A or B is the probability of A plus the probability of B if A and B are mutually exclusive. But in general, the probability of A or B is the probability of A plus the probability of B minus probability of A and B. Remember, that's a joint probability. Okay? But again, by definition, the joint probability of A and B is 0 if A and B are mutually exclusive. These are things that can't happen together. Now, certain things can happen together, and you have to know whether they're mutually exclusive or not. Now, we know that the probability of getting a head or a tail is the probability of the head plus the probability of the tail. And you don't have to worry about that joint probability of head-tail, because that's 0. It doesn't exist. That's why the probability of getting a head or a tail is a half, probability of the head, plus the probability of the tail, which is a half, and that equals to 1. This Venn diagram here is a very simple way of seeing how A and B look when they're mutually exclusive. See the top box is the A and the B, and they're not touching each other because they're mutually exclusive. Notice in the bottom box we show A and B that kind of overlapping because they're not mutually exclusive. So notice you have an A and there's an intersection. That's an A and B there where they both intersect. So that's called the probability of A and B. That's the intersection of A and B, and the Venn diagram makes you see it very clearly. And that means they're not mutually exclusive. From the Venn diagrams, you can also see the probability of A prime, which means not A. You read that not as prime, but as not A, is 1 minus the probability of A. And the probability of not A or not B is 1 minus the probability of A and B. Okay, these examples will make it clear. Suppose you go to college, we allow double majors. Okay, you can double major, 2 majors. So we know 10% of the students are majoring in accounting, that's A. 15% of the students are majoring in business, B. 3% are double majors, A and B. Okay, so what's the probability of being an accounting or a business major? Here's a little hint. They're not mutually exclusive, because we just said it, you can be a double major, A and B. That means it's an intersection. So the answer to that is the probability of A or B is 0.10 plus 0.15. Notice we have to subtract the 0.03. And that works out to 0.22. If you didn't subtract that 0.03, you'd be double counting the accounting and business majors, because they show up in both lists. Think of it as 2 lists. The accounting list shows them. The business list shows these 3%. You don't want to count the 3% 2 times, and that's why we subtract it out. So this is a very good illustration of the law of addition.
The rules of multiplication are used to compute joint probabilities, which we know from this previous slide this is the probability that event A and event B occur together, that they both occur. Like the example we just saw, the probability that someone is both an accounting major and a business major. That's a joint probability. Well, first let's look at a very specific case, then we'll go to the general case. In the specific case, if the 2 events we're talking about are independent of each other, in other words, that knowing something about one having occurred doesn't change the probability that the other one occurs, then we just multiply the probabilities. And for example, if we're tossing a coin, and let's say it's a fair coin, you toss it once and you know that a head occurred. What's the probability that you'll get a head on the second toss? Well, it was 50% on the first toss, it's still 50% on the second toss, it's still 1 out of 2, because each toss is independent of what happened before. So with independent events, we just multiply the probabilities of the events. Here are some examples to help you understand what independence is. Suppose I take a student at random from our college population, and I tell you that student is male. What's the probability that that student has blue eyes? Well, that ought to be just the same as the probability that a student has blue eyes without knowing whether the student is male or female, because there is independence. There's no relationship between sex and eye color. On the other hand, if I take a student at random and I say that that student is female, now what's the probability the student's over 6 feet tall? Well, knowing that the student is female, that should make a difference. And it will change the probability from the simple probability of just any student being over 6 feet tall. And, you can find all kinds of other examples that are similar that help you make the case. Here's the general formula for multiplication. If we don't know that events A and B are independent, or if we know for sure they're not independent, then we can compute the joint probability of A and B by taking the probability of A given B multiplied by the probability of B. You always multiply by the event after the given. We could do it the other way around too. We could get the probability of B given A and multiply by the probability of A. That'll also give us the joint probability of A and B. It all depends on what you have and what you're trying to compute. And of course we know that the probability of A given B is a conditional probability. If the two events are independent, as we just saw, then the probability of A given B is just the same as the probability of A. And so the general formula for multiplication in the case of independent events will turn into the probability of A times the probability of B, which is exactly what we had before for independent events. So the two formulas for multiplication are not different at all. They're exactly the same. It all depends on whether the events we're looking at are independent or not. Sometimes we're going to want to use these formulas in order to prove that the events are independent or not independent, and we can. If we have the probabilities, say, the conditional probability of A given B, and we have the simple probability, the probability of A, and they're not equal to each other, then we can say these events are not independent. Because if they are independent, knowing something about B would not change the probability that A occurs. And similarly, we can use the multiplication rule to determine if two events are independent. If the probability of A times the probability of B is exactly equal to the joint probability of A and B, that's proof enough that events A and B are independent of each other. And finally, we have the rule for conditional probability, or how we compute conditional probability. All we do is we're just turning around the previous rule from number 4b, we actually have it on the same slide. If the probability of A and B is equal to the probability of A given B times the probability of B, then if we need to compute the probability of A given B and we have the other terms, that's exactly equal to the joint probability of A and B divided by the probability for the event after the given, or divided by the probability of B. We're not going to cover Bayes' theorem in this course. It's an optional topic, so we're not going to worry about it for now. Here we have a simple example to start. We're looking at readership of two different newspapers, the New York Times and the Wall Street Journal. And in this particular village, the probability that an individual reads the New York Times is 0.25, because 25% of the population does. The probability that an individual reads the Wall Street Journal is 0.20. The probability that an individual reads both the New York Times and the Wall Street Journal is 0.05, or 5%. So the question is, what's the probability of an individual being either a New York Times reader or a Wall Street Journal reader. So that's the rule of addition that we're going to be using. The probability of being a New York Times reader or a Wall Street Journal reader is equal to the probability of reading the Times, 0.25, plus the probability of reading the Journal, 0.20, minus the probability of reading both of them because we don't want to count these people twice. And that's 0.05. So 0.25 plus 0.20 minus 0.05 is equal to 0.40. So 40% of the population reads something. Here we see the same thing laid out in a Venn diagram, and you can see the joint probability in the middle, and actually what you see here is the same data you saw before, but instead of being laid out looking like probabilities or percentages, it's on the basis of 100. So suppose we have 100 people selected at random from this village. 5 of them would read both the New York Times and the Wall Street Journal. 40 of them would read at least one, would read one of them or anything. And then there are 60 people out of the 100 that don't read either one. Sometimes your probability problems that you do for homework will ask you for various different types of probabilities. And here you have an example of some of the different types of questions that you could be asked. Another way to look at problems like this, where you have a set of probabilities and then you're asked a lot of questions about them, is to put them into a table of joint probabilities. We'll see more of this later on, so we're not going to work with this now. It's just to show you that this is an alternate way. In some problems, it's actually the much better way of solving the problem.
It's very important to understand the difference between independence and mutually exclusive events. Don't confuse them. A lot of students tend to do that. Mutually exclusive simply means that the probability of A and B is 0. They can't occur together. It's more of a physical thing. You can't have a head and tail at the same time. You can't pass and fail the course at the same time. Those are mutually exclusive. So simply put, it's just the probability of A and B is 0. Independence means something altogether different. Has to be the effect of, let's take B on A. Does knowing B have any effect on A? If knowing B has an effect on A, then we could say they're not independent. If knowing B has no effect on A, then they're independent. So independence is more like a concept of unrelated, uncorrelated. So the example we have here is waist size and gender. Are they independent of each other? So suppose you know that somebody who's an adult has a 24-inch waist. Would that give you a hint as to whether that person is male or female? Well, we can figure that out, because we know that the probability of having a 24-inch waist, given that you're female, is not the same as the probability of having 24-inch waist in general, or probability of 24-inch waist given that you're male. So when you do probability of 24-inch waist in general, you're combining males and females. So the minute I know that somebody has a 24-inch waist, I'm quite certain that they're highly likely to be female. Very few men have 24-inch waist. So that's another way of seeing this idea of relationship and independence. So again, if the probability of A given B is the probability of A, then A and B are independent. If the probability of A given B is not A, not the probability of A, then there's some kind of relationship here. They're not independent. Researchers are always interested in whether two events are independent or not. For example, is there a relationship between lung cancer and smoking? Or are they independent of each other? Well, we know the answer to that one. I don't think anyone in this room believes that they're independent. Certainly smoking has an effect on lung cancer, and people who get lung cancer generally have been smokers. All right? Is there a relationship between occupation, how long you live? Talk about longevity. Or are they independent? Well, studies show that occupation does affect your lifespan. Librarians, I think, have the highest lifespan of them all. Coal miners and drug dealers have the very shortest lifespans. So you see there is some kind of relationship. And again, insurance companies will use that information when they sell you life insurance. They look at your occupation too. Is there a relationship between salary and how slender you are? Well, studies are showing that women who are very slender get much more money. Unfortunately, I mean, this is one of these kinds of discriminations, but there have been studies done on this. What about how many dates you get and your hair color? Well, believe it or not, somebody studied that. I think on the sites like eHarmony and others, and they found that women who had blonde hair had more dates on these sites than women who had other color hair. So you see, this is the kind of thing researchers want to know. You're not going to win the Nobel Prize for finding out what doesn't cure cancer. You're going to win the Nobel Prize if you find the cure for cancer or the cure for Alzheimer's. We're always looking for relationships. So these tests for independence, which we're going to learn soon, are very valuable to statisticians. Now, in this example, we're looking at a contingency table. We're looking at smokers, non-smokers, and whether they had died of cancer or not. We're looking at a sample of 1,000 people. Those are frequencies in the table. And the way you read that is in the sample of 1,000, 100 people were smokers who died of cancer. Notice there were a total of 400 smokers. You get that from the marginal total. 300 smokers did not die of cancer. Among non-smokers, we had 50 that died of cancer and 550 that didn't die of cancer. Incidentally, those totals on the side, what we call the marginal or simple probabilities, are useful. 150 people died total in this sample of cancer, right? All the way on the right. 850 did not have cancer. We had 400 smokers in the sample, 600 non-smokers, and that's how we had 1,000 people. If you divide through by 1,000, then you can get a joint probability table. But you see the joint probabilities in the bottom. You take 100 divided by 1,000, you get 0.10. That's the probability of C and S. If you want to know the probability of not C and S, 300 over 1,000, that's 0.30. If you divide 50 by 1,000, that 0.05 is the probability of C and not S. And if you want the probability of not C and not S, that's the 550 over 1,000, that's 0.55. That gives you the joint probabilities. If you take those marginal totals and divide them by 1,000, the probability of C, 150 over 1,000, is 0.15. The probability of not C, 0.85. That's 850 over 1,000. Now look at the column totals. There are 400 smokers. Divide that by 1,000. The probability of being a smoker is 40%, 0.40. The probability of being a non-smoker is 60. The researcher looking at this table would want to answer the question, are smoking and cancer independent or not? Well, several ways to answer it. Here's one way to do it. We look at the probability of C, and we see if it's equal to the probability of C given S. And if you want, we can also look at it with the probability of C given not S. Well, the probability of C given S is cancer given that you're a smoker. That's the probability of being a cancer and smoker over probability of smoker, or 0.10 over 0.40 of 25%. So once we know you're a smoker, there's a 25% chance you're going to die of cancer. Look at the probability of C given not S. That's the probability of C and not being a smoker, not S, over the probability of not S. That works out to 0.05 over 0.60. That works out to 0.083, 8.3%. If you're a non-smoker, there's an 8.3% chance of dying of cancer. The probability of cancer, the simple probability, that's kind of an average. It averages altitude. It's a weighted average, actually. Remember, there were more non-smokers than smokers, so it's not a simple average. That's 0.15. But looking at all three probabilities, you just have to look at two of them, but looking at all three, you can see what's going on. In general, there's a 15% you're going to die of cancer. If you're a smoker, it's 25%. If you're a non-smoker, that probability is 0.083. So researchers looking at these numbers will simply state that smoking and cancer are not independent. There is actually a relationship between the two. And this is how you win the Nobel Prize, by finding relationships. This one, of course, you're not going to win the Nobel Prize for. I think everybody knows this one. Here's another way you can actually determine that cancer and smoking are not independent. If cancer and smoking are independent, then the probability of C and S is equal to the probability of C times the probability of S. Remember, that was the formula for independent events. we did with A and B. The probability of A and B is the probability A times the probability of B if they're independent. Well, the probability of C and S, we know, is 0.10. Is that equal to the probability of C of 0.15 times the probability of S of 0.40? Well, 0.10 is not equal to 0.06 on this planet, so we conclude that cancer and smoking are not dependent. In any event, if you want to do this properly, it's always useful to set up a joint probability, which we'll show you on the next two slides. Okay, here we see the joint probability for the same data we had before. Remember, you divide through by 1,000, and those frequencies in the 4 cells, remember the cancer and smoking cell, we have 4 cells, divide through by 1,000, you get a joint probability table, and the marginal totals we divide through by 1,000 too. And notice you got everything there. The way you read it, that's an and always. The probability of being a smoker and cancer is 0.10. Cancer and non-smokers, 0.05. Smoker and not cancer, 0.30. And the non-smoker without cancer is 0.55. And all these probabilities add up to 1. You see that? It's very useful to set up this joint probability table because you can see everything you want. And again, the marginal probabilities are the row and column totals. Okay? So look at the same problem set up with a joint probability table. It's a lot easier to solve. Now again, here we have the joint probability set up nice and neat. Everything is here. And notice you get the joint probabilities in the center of the table, the marginal probabilities are in the margins, and a conditional probability is computed simply by dividing the joint probability by marginal probability. So the probability of C given S is the probability of C and S, that's at 0.10, divided by the column total, the marginal probability of 0.40 or 0.25. Here's another example with gender and beer drinking. Okay, we have beer drinker for B. B prime means not a beer drinker. We have M and F for male and female. And we see the frequencies here, 450, 450, 357. We turn into a joint probability table by dividing through by 2,000. There's 2,000 in the sample. And you see all the joint probabilities, they're all given, right? For example, the probability of being a male who drinks beer. Notice B and M is the same as M and B. A man who drinks beer would be, that probability would be 0.225. A female who drinks beer, that's 0.175. A man who doesn't drink beer, that's 0.225 also. And a female who doesn't drink beer is 0.375. And we have these marginals there. Marginal probability. So they ask you, well, what's the probability of somebody being a beer drinker in this town? You say 40%. That's the probability of B. That includes men and women together. They say, well, what's the probability of somebody being a male in this town? Well, in this town, 900 out of 2,000, or 0.45, are males. So you see, again, in the joint probability table, everything you need to know is right there. Now, here's the conditional probabilities. So given that an individual is male, what's the probability that that person is a beer drinker? That's the probability of B given M. And that's the probability of B and M over the probability of M. That works out to 0.225 over 0.45, or 50%. Once I know you're a male, 50% chance in this town that you drink beer. What about if given that you're a female? What's the probability you're a beer drinker? Well, that's the probability of B given F. That's the probability of B and F over the probability of F. Again, we take the joint over the marginal. So in this case, the B given F is 0.175, that's beer and female, over probably being female in this town, which is 0.55, and that works out to 0.318. Are beer drinking and gender independent? Well, we know the probability of beer drinking is 0.40. It's a weighted average, again, of those above numbers. Notice if you're a male, we know there's a 50% chance you drink beer. If you're a female, it's a 0.318, about a little less than, well, let's make it exact, 31.8% chance that you drink beer. Clearly, there's some kind of relationship, and we know men are more likely to drink beer than women. Again, the 0.40 is a weighted average of the two. But again, the researcher looking at this data would say beer drinking and sex are not independent. There's some kind of pattern. And once I know that you're a man, I know you're more likely to drink beer. Okay? In this problem, we're looking at a marketing example. Dove soap. A lot of you may use that soap. And we want to know, is there a relationship between gender, male, female, and use of Dove soap? So we have this contingency table here. Notice we took a sample of 1,000 people in some town, and here's what we found. Men who use Dove soap, males who use Dove soap, there were 80 out of 1,000. Females who use Dove soap was 120. Men who didn't use Dove soap, 320. And females who didn't use Dove soap, 480. All the joint probabilities are on the bottom there. So the probability of DNM, which by the way is the same as M and D, is 8%. The probability of DNF is 12%. Probability of not DNF is 0.48, and we have the marginal total. So the 20% chance of using Dove soap, 80% don't use Dove soap. That's probably not D. Probability of M is 40%. 40% chance you're a male in this sample. There's 40% males, and the probability of female is 60%. So we have all the important probabilities computed for you. Well, the marketing researcher might want to know whether gender and use of Dove soap are independent or not. Well, here's what you find out. The probability of being a Dove user is 20% in this town. The probability of D given M, that's Dove user given that you're male, that's 0.08 over 0.40, which is also 20%. The probability of D given F, remember that's D and F over the probability of F, that's 0.12 over 0.60, that's also 20%. Guess what? They're independent, doesn't matter. Knowing the gender of the person doesn't affect their use of Dove or not. We know for sure that it's 20%, whether you're male or female, so that's independent. If you want to do it a different way, you can we know that the probability of M and D, the joint probability, is 8%. Is that equal to the probability of M times the probability of D? Well, 0.08 is equal to 0.40 times 0.20. So yes, the two events M and D are independent of each other.